This question says the half-life of radium is 1,690 years. 5 grams are present now. Determine the following. How many grams will be present in 100 years, and how much time must pass so that there are fewer than 3 grams remaining? So the half-life is 1,690 years. What can we say about this? We have some initial number, and we have a growth factor that we're dealing with. So the amount present, P, is the initial amount, which I usually call C, e to some growth factor, KT. Now, we know that the half-life is 1,690 years. The initial amount, notice if T equals 0, so what is P of 0? P of 0 is C e to the K times 0, which is C e to the 0, which is C times 1, which is C. So initially there are C grams, pounds, tons available, whatever it may be. So the half-life is 1,690 years. So when T equals 1,690, P is half of the original. P is half of C. So we can set up our equation this way. P is 1/2 of C. The initial concept is C. E to the K is what I want to find. And T is 1,690. Now you've got to be very careful with significant figures here. If I divide both sides by C, you will notice my next line is 1/2. The C's go away, equals E to the K times 1,690, or 1,690K. So I'd like to know what that growth factor is. I'd like to solve for K. Let's go ahead and take the logarithm of both sides. Logarithm of the left side equals logarithm of the right side. So logarithm of 1/2 equals logarithm of E to the 1,690K. This exponent can come down front, and I get natural log of 1/2, which you could think of as natural log, negative natural log 2. Not really necessary though. Natural log 1/2 equals 1,690K times the natural log of E. The natural log of E is just 1. So we'll say the natural log of 1/2 is 1,690K. So if I divide both sides by 1,690, natural log of 1/2 divided by 1,690 equals K. So let's get that in the graphing calculator. So upstairs, natural log 1/2. Divided by, on the bottom, 1,690. And I get that very, very small number. So I'm going to store that in K. But it's negative, converting back from scientific notation. K is negative 0.00041015, approximately. You don't want to round too early or you're going to have some difficulty. But I've actually got all of my decimals saved in for K there. Now, what did I want to answer? I have a value for K. I know what C is. C, my initial value, C was what? Or I don't think I have said that yet, actually. So let's go back and look at the question. 5 grams were present now. How many are present in 100 years? So if 5 grams are present now, that means C equals 5. Find P when T is 100 years. It's going to be pretty close to 5 because it takes almost 1,700 years to lose half. So in only 100 years, it's not going to lose very much. So remember we said our original model was P, the amount present, to C, the starting amount, E, K is our growth factor, T is our time. So P we want, C here is 5, E to the K that we just had was negative 0.00041,015 T. But I want to find P when T is 100. So what is P of 100? 5e to the negative 0.00041,015 times 100. So that is certainly a job for the graphing calculator. So let's go do it. So what do I have? I have 5 times e to the, and then I'll use parentheses here, negative. I'll go ahead and I'll type it out the first time, then I'll show how I saved it in the calculator. 0.00041,015 times 100. So 5e to the kt, k is that negative 0.004, t is 100, and what do I get? I get 4.799 approximately. But I want to go ahead and I want to show you, because remember I stored k in the calculator. So I'm going to try it one more time with just using k instead. You'll see the advantage of doing it that way. 5 times e, which is second logarithm, to the k, so just type alpha k, since I stored that whole thing in k, times 100. And I expect I will get a number very similar to 4.799. And I do, indeed. I'm good out to 1, 2, 3, 4, 5 decimal places or so. So that's how much remains at the end of 100 years. We started with 5 grams, now we're at 4.799. Not much decayed after 100 years. And then the last thing I need, how much time must pass so that there are fewer than 3 grams remaining? So what is that saying? Find t when p equals 3 or less than 3. What am I going to say? Find how much time must pass. Find t when p is essentially 3 is what we're looking for. So again, p equals ce to the kt. We know c is 5, so let p be 3. C is 5. E to the k, that's that nasty number, the negative 0.00041,015 t. That's what I'm going to try to solve for this. So let's divide both sides by 5. The left side is 3/5 or 0.6. So we get 0.6 is e to the negative 0.00041,015 t. Let's hit both sides with a natural log. So natural log 0.6 equals natural log e to the negative 0.00041,015 t. And we know that with logs, you can pull the exponent down in front. So this whole thing comes in front of the logarithm. So where does that lead me? Now we are at what? We are here. So natural log 0.6 equals pulling that down in front, negative 0.00041,015 t, natural log e, but natural log e is just 1, so that's not going to add anything to our discussion. Natural log 0.6 equals negative 0.00041,015 t. Divide both sides by what's multiplying t. We which is negative 0.00041,015, negative 0.00041,015, and then what does t equal? How much time must pass so that there's less than 3 grams remaining? Again, let's do this on the graphing calculator. Upstairs, I have natural log of 0.6. Downstairs, I'll type it the long way first again, negative 0.00041,015. And what do I get? 1,245 and a half, basically, years. If I didn't want to type all that out, remember this is just K, is it not? So I could have just said natural log 0.6 divided by K. I had stored that in K. And I should get essentially the same thing, about 1245 and a half. So how do we conclude this? 1245 and a half years must pass, approximately. 1245 and a half years must pass so that fewer than 3 grams remain.